think of, in the case of a heat equation, how does the finite difference discretization being used? Okay, so here we have a function of space and time, right? So let's discretize space first. Okay, so let's have a spatial domain from L to R discretized into these grid points. And L and R are between L and R are the domain which I solve my differential equation. Suppose my solution at a particular time looks like this. A finite difference discretization only stores the solution at these grid points. Right? That means I'm going to represent my function u of x and t is represented, by this u1 of t, u2 of t, etc. un of t, where the value of the function at the first grid point is u1 of t. The value of the function at second grid point is u2 of t. And if I have n grid points, the value of the function at the last grid point is un of t. So this is a vector function of time. Okay? And the goal of finite difference for the heat equation is to derive a method of solving for this a vector function of t. And the way to do that is to derive an ordinary differential equation that represents that evolution. Right, so we have basically converted a partial differential, basically a function of two variables, x and t, into multiple functions of only one variable. I mean, n may be large. For some problems, n may be millions or billions. But anyway, these are finite numbers. I have converted a function of space into a vector of space. And next is to how do we derive, now we have get rid of the partial derivative. How do we derive du1 dt equal to what? du2 dt equal to what? Etc. If we can derive these, we know how to solve this using methods of ordinary differential equations, right? Okay, so this is the job of finite difference approximation. This is because let's say dui dt, let's say I is an integer, it means the ith grid point, is actually the partial derivative of u at the ith grid point. Let's say xi is the location of the ith grid point, t, partial t, right? And if you look at the partial differential equation, it is equal to kappa times the second derivative of u with respect to x at this grid point. So the task of finite difference discretization is to approximate the spatial derivative with something that does not involve derivatives. And in particular, in this case, we approximate this as u of I plus 1 minus 2 times ui plus u of I minus 1 divided by delta x squared. Now, why do we do this? So first of all, if there is a good justification of doing this, it's great. Because now I have converted the partial differential equation through an approximation to a set of ordinary differential equations. If I know the current state of u1, u2 up to un, I know the time derivative of the same set of u1, u2 to un. And if I take a small time step, if I take an infinitesimal delta t, I know the value of the function at the infinitesimal delta t ahead. And I can use methods of ordinary differential equation, like forward Euler, right? How many people remember what forward Euler is? Not very good. So forward Euler means like if I take ui of t plus delta t, right, at a slightly later time, I'm going to approximate the time derivative as a finite difference in time. I take the difference between ui at a little bit further in time minus ui at the current time divided by the delta t is equal to ui plus 1 at t minus 2 ui at t plus ui minus 1 at t divided by delta x squared. And where delta x is the difference between two grid points. Right, it's the spacing between xi and xi plus 1 and also between xi minus 1 and xi. Okay, so if I can use forward Euler to solve this set of ordinary differential equations, this becomes ODEs. Then I can start from the initial value at t equal to 0. I can update the solution to t equal to delta t, and then update the solution to t equal to 2 delta t, etc., etc. And I can solve the equation for as long time as you want, given enough computational time. All right, and of course there are other methods of solving ordinary differential equations, like backward Euler, trapezoidal rule, and Runge-Kutta methods. I hope that sounds familiar with you. If not, you need to review your ordinary differential equations. And in MATLAB, MATLAB comes with some pretty good ODE solvers. And if you look at go to MATLAB, type help ODE 45. That's one of the most popular ODE solvers in MATLAB. If you just type that in MATLAB, you're going to get a lot of help. Right, so you're going to see a lot about like how to use ODE solvers like that. But what I want to say is that if you reduce the PD into a set of ODEs, we're in pretty good shape. Okay. And why can we do that? Why can we do that? Let me. Okay. We approximate the spatial derivative with this thing we call finite difference. And the justification of such approximations is through Taylor series. I see people nodding their heads. That's good. So a Taylor series basically represents the solution at a neighboring grid point as the solution at the current point plus some derivative terms. Okay, let me do it over here. I'm gonna keep my annotations. Let me insert a new slide and go back again. Oops. Duplicate slideshow. Okay. So the solution u at I plus 1 through Taylor series analysis is equal to ui plus a delta x times the partial derivative of u at I plus half of delta x squared times the second derivative of x at I plus a higher order terms I'm going to write as O delta x cube. Is that familiar with you? Taylor series analysis. A huge fraction of numerical PD is based on Taylor series analysis. So you should be able to, like a few lectures ahead, you should be able to write down Taylor series analysis like this without even thinking. And ui minus 1 would be equal to ui minus delta x times the same derivative, first order derivative, plus delta x squared. So this one is plus, this one is minus. For all even derivatives, it is the same sign, is plus. For all odd derivatives, if you go backwards, it is going to be minus. And again, this is plus O delta x cube. And of course, ui minus 2ui equal to minus 2ui. So if you add all these three up, this cancels. All right? This cancels. And the leading term is this. So ui plus 1 plus ui minus 1 minus 2ui is equal to delta x squared times partial derivative. This is the second derivative we want to approximate, plus O delta x cube. And O delta x cube means a bunch of terms that scales with delta x cube, or even delta x fourth, delta x fifth, etc., etc. All right. Okay. Now, if we divide by delta x squared, we cancel this, and this gets divided by delta x squared. So basically, we are saying that the second derivative at ith point can be approximated by this finite difference plus O delta x, because cube over square is O delta x. What does this mean? This means as delta x goes smaller and smaller and smaller, this term goes smaller and smaller and smaller. If you choose a delta x that is small enough, this term is going to be small enough so that I have a good approximation. All finite difference methods aims to derive these kind of finite difference approximations to all kinds of spatial derivatives, such that as delta x goes smaller and smaller and smaller, the approximation becomes better and better and better. In other words, the error of the approximation like this goes smaller and smaller. And the order of this approximation, as you have raised up, is the order is how fast this approximation error goes to 0 as delta x shrinks. For example, if I can write this as O delta x to the 8th, let's say, then I get an awfully good approximation. Because if I only have O delta x, then as I refine the grid into half of the spacing, I can only expect the approximation error to go down by a factor of 2. But if I have 8th, then I know every refinement by a factor of 2 gets me a 64th. It's a factor of 64 better approximation error. That's very good, right? Okay, so this is the order of the approximation. Like we want something like this, right? Okay, of course, as you want the number, you want the order, so this is the order. As the order gets higher and higher, the method becomes, the derivation becomes more complex, the implementation may becomes more complex, and things like that. So there is, of course, going to be a